Hello everyone, I'm Yue. It's my pleasure today to present you our ORCSolver, which is an efficient solver for adaptive GUI layout with all constraints. Previously, designers have to create different layouts for different screen sizes and orientations to get desirable results. This makes GUI design more time-consuming. At last year's CHI, we introduced all constraint GUI layouts to specify adaptive GUIs for screens with different sizes, orientations, or aspect ratios using only a single layout specification. An all constraint is a disjunction of multiple constraints, where only one needs to be true. ORC layouts also unify conventional constraint-based layouts with flow layouts. Modern GUI layouts often use constraints to align widgets or add other restrictions. However, in constraint-based layouts, the layout topology is fixed, which means that once the designer is done with the layout design, widgets will have the fixed positions, so they cannot move around anymore. Web layouts are often flow-based. Whenever the screen size changes, items can reflow down the page in the same way we read a document. However, flow layouts do not allow designers to restrict the positions and sizes of items relative to each other. Unifying these two kinds of layouts with all constraints makes GUI design less time-consuming, easier to maintain, and to keep consistent. Unfortunately, adding all constraints is like adding more potential combinations to the solution space of feasible layouts under the given constraints. So solving all layouts with current solvers is time-consuming, and the needed time increases exponentially with the number of widgets and constraints, as they need to evaluate very large numbers of potential combinations. To address this challenge, we propose ORCSolver, a novel efficient solving technique for adaptive ORC layouts based on a branch and bound approach with heuristic preprocessing. Our ORCSolver simplifies ORC specifications at runtime and can solve ORC layout specifications in approximately linear time in practice, which allows us to optimize layouts with dozens of widgets at near interactive rates. ORCSolver is the first solver that can solve complex realistic layouts made of linear constraints, flows, and their combinations efficiently. ORCSolver is based on a branch and bound approach. It is very time-consuming to explore the solution space, as there are many branches we need to search with branch and bound. So we make it feasible by removing branches with heuristics. Constraints are low-level and hard to specify manually. ORC layout patterns can be represented as layout types, so we provide a user-friendly formal notation to specify ORC layouts that can be fed into our ORCSolver and help to formalize solving strategies. Users can specify layouts using a simple API based on this formalization. We formalize fixed horizontal and vertical alignments as row and column layout types, and flow layouts as horizontal flow and vertical flow. The horizontal flow could contain toolbar widgets. In the horizontal flow layout, we use the all constraint to the right of the previous widget, or at the beginning of the next row between each consecutive pair of widgets. The ORC layout patterns can be combined. For example, this layout uses a column layout dividing the window into a horizontal flow and the lower part, which is a row layout containing a vertical flow and a text box. Our notation can also specify how layouts change in response to changing UI sizes. For example, we define a pivot layout to encode more flexibility into the layout design. The pivot layout allows the solver to turn horizontal arrangements into vertical ones and vice versa using all constraints. It could represent the all constraint column or row, or the all constraint horizontal flow or vertical flow. By default, the pivot layout only modifies its first sublayout. By using pivot, the column can be turned into a row to adapt from a landscape orientation where the toolbar is at the top to a portrait orientation where the toolbar is on the left. Internally, the solver breaks the layout down into two alternatives. Now we describe our ORCSolver. We define an objective function to evaluate layouts. To create a balanced layout appearance, our objective function is the sum of the L2 loss of the deviations between preferred and resulting sizes. It is a least squares approach that reduces deviations by minimizing their squares. In addition, deviations from the preferred widget sizes can be scaled by widget weights. To start, ORCSolver constructs the branch and bound tree for a layout based on its formal ORC layout notation. The tree is initially constructed as a one-branch tree, containing sublayouts in the order in which they are chosen for processing based on their firm edges. Starting from the root node, as ORCSolver goes down the tree, it adds more and more constraints to the constraint system. Each node in the branch and bound tree has a layout specification containing variables, constraints, and objectives. As ORCSolver goes down the tree, it clones the specification from the parent node and adds simplified variables, constraints, and objectives for the current sublayouts based on the preprocessing results such as heuristics for flows. ORCSolver solves the specification using a quadratic solver in the leaf node to calculate the overall loss value. Here we explain the main steps of the solver using a simple example. In this example, the horizontal flow layout may be a toolbar, and with the pivot, we allow the solver to place the toolbar either at the top or on the left. The solver processes the first alternative, the toolbar at the top first. Starting from the root node, as ORCSolver goes down the tree, it adds more and more constraints to the constraint system. ORCSolver solves the specification using a quadratic solver in the leaf node to calculate its overall loss value gotten from the objective function. After finishing exploring one alternative, it backtracks up to the pivot node and processes the other alternative. When hitting a new leaf node, ORCSolver compares its loss with the currently best solution. If smaller, then the leaf becomes the new best solution. The solver often cannot quickly search all branches, so we need to limit the search to branches that may improve the solution. We achieve this by conducting a discrete gradient search for better solutions. The search uses parameters of the layout, such as the number of rows a horizontal flow is broken into. The overall idea of our approach is to first try the local best fit with the preferred number of rows or columns in the flow at each flow node, and then gradually explore into the direction of decreasing overall loss by adding new branches to process for both smaller and larger numbers of rows or columns. In this example, the solver starts with the preferred number of rows to process the horizontal flow and get a good local fit. Then it goes down the tree and starts with the preferred number of columns C for the vertical flow. It then continues to go down to the leaf and stores the result of this branch as the currently best solution. Then the solver backtracks in the branch and bound tree to the vertical flow node and tries other alternatives that may lead to a better solution. It starts with the alternatives with fewer columns, in the order of C-1, C-2, etc. When it processes C-1 branch, if the loss is smaller, we update the currently best solution accordingly and process the next vertical flow alternative with C-2 columns. If that is not better than the previous branch, ORCSolver stops trying even fewer columns, since that would continue the trend of a narrower vertical flow and lead to worse results. Analogously, it also tries increasing numbers of columns starting from C+1 until that also increases the loss. After getting the best solution for the vertical flow, ORCSolver backtracks to process the horizontal flow. Similarly, our ORCSolver gradually explores in the directions of decreasing overall loss values. For each branch created for the horizontal flow, it proceeds down the branch following the same process for the vertical flow as in the main stem. By backtracking and exploring possible better solutions, it optimizes the solution for the layout. Solving all constraints and soft constraints is more challenging than solving hard constraints due to the combinatorial explosion. ORCSolver uses heuristics for the different ORC layout subtypes that reduce the number of all constraints and soft constraints by either removing them or changing them into hard constraints, while at the same time ensuring that the simplified constraint system is equivalent to the original one. During branch and bound, instead of solving a large number of all constraints directly, we apply heuristics, especially for flows, to make it computationally tractable. In the following, we describe the heuristic algorithm ORCSolver uses to locally optimize org layout specifications in order to reduce the number of constraints. For a simple horizontal flow based on the widget's minimum, preferred, and maximum sizes, ORCSolver first uses a simple greedy heuristic to compute the minimum, preferred, and maximum numbers of rows. The potential numbers of rows cannot be beyond the minimum and maximum, so we get the potential range of rows in the flow. Given a specific number of rows, every time before starting a new row, ORCSolver calculates the remaining available widths in the flow and computes the average deviation from preferred widths for all the remaining widgets. Then it keeps adding the next widget using its preferred width plus the average deviation to the optimal arrangement of widgets in the flow. To fill a row without leaving gaps, ORCSolver redistributes the sizes of widgets evenly over the available widths by minimizing the sum of squared deviations to create a balanced appearance. Here we describe several heuristics for different org layout patterns. Each pattern is defined as a layout type in our formal notation, so that users can apply them directly through the provided API. Each heuristic is an extension of the heuristic flow algorithm to accelerate the solution for the pattern. We show the efficiency of ORCSolver solving each org layout pattern through comparison with 3 other solvers in logarithmic graphs. The blue line in the plot is our timing result. ORCSolver is the fastest solver among the 4 solvers and can solve org layout specifications in approximately linear time in practice, while other solvers need exponential computation time. The next layout pattern is connected flow. If 2 flows are connected, widgets in one can move to the other. In this case, given the target number of rows in the first toolbar, ORCSolver flows all the widgets in both toolbars into the first flow and stops when we reach the target number of rows, and assigns the remaining widgets to the second toolbar. It then applies the algorithm for simple flow to optimize both toolbars. For flowing around a fixed area pattern, ORCSolver divides the sublayout into 3 areas: upper, middle, and lower areas, where the middle area has a horizontal flow with a gap in the middle. Then it processes the 3 areas as 3 connected flows. In balanced flow layout pattern, all rows contain the same number of widgets. To solve this, ORCSolver computes all the factors of the total number of widgets in the flow sublayout, and then explores the different factors through branch and bound, using appropriate number of rows in the flow algorithm. In optional widgets pattern, widgets in flows can be optional. ORCSolver first sorts all the optional widgets by ascending weights and processes the flow row by row. If the total sum of widget widths remaining to the flow is greater than the empty space in the flow, it tries removing the optional widgets with the lowest priority, and then continues to remove widgets in ascending order of priority as long as it reduces the loss. If there is more available space for the remaining rows, check we have removed optional widgets which can be added back in. ORCSolver keeps adding back optional widgets with the highest priority, as long as it does not increase the loss. Alternative positions can be defined for widgets or sublayouts. For example, a top toolbar can be moved to the left or vice versa when the screen size changes. The preferred alternative is given a higher weight. The final position is determined by branch and bound, minimizing the objective function. In conclusion, ORCSolver is an efficient solver for adaptive GUI layouts, integrating branch and bound, greedy optimization, and quadratic programming. It overcomes the main performance bottleneck for using all constraint layouts, and solves org layouts efficiently at near interactive rates, even for large numbers of widgets. ORCSolver can be used for any layout that can be represented with linear constraints or flows, which includes almost all commonly used layout models and document layout patterns. So our ORCSolver is a general contribution, and open source code is available online. In the end, I appreciate all the support from my 3 advisors. Thank you, and try out our code.